Hello everybody, this is Brandon, and today I will be walking you through problem number 17 on chapter 20, Physics B AP. Number 17 reads, to monitor the breathing of a hospital patient, a thin belt is girded around the patient's chest as in figure P 20.17. The belt is a 200 turn coil. When the patient inhales, the area encircled by the coil increases by 39 centimeters squared. The magnitude of the Earth's magnetic field is 50 microtesla and makes an angle of 28 degrees with the plane of the coil. Assuming a patient takes 1.8 seconds to inhale, find the magnitude of the average induced EMF in the coil during that time. Diagram-wise, here's what we're looking at. We have the original size of the belt before the patient inhales, at which the area is X. 1.8 seconds later, that belt will have expanded to X plus 39 centimeters squared. I'm going to go ahead and change that to 0.0039 meters squared. Alright, the first step in solving this equation is choosing an x. It can be anything you like it to be. I decided to keep it simple, 0.002 meters squared. Our patient is very thin. So then 0.002 meters squared plus the 0.0039 meters squared, 0.0059 meters squared. So I wrote down some other notes that we should know. First of all, n is 200 turns. That was given to us in the problem. And theta is actually 62 degrees. Now the book told us that the theta between the plane and the magnetic field was 28 degrees. However, we do not want the angle between the plane and the magnetic field. We want the angle between the magnetic field and the axis of the circle instead of the plane of the circle. Because those are always perpendicular, 90 degrees minus 28 degrees is going to be 62 degrees, so theta is 62 degrees. So we came up with the area initial as 0.002 meters squared. We know the area final is 0.0059 meters squared, and again, you can put in whatever you want as long as there's a difference of 0.0039 meters squared. Again, given to us was the magnetic field, which is 50 microtesla, or 50 times 10 to the negative 6 Tesla, and then we know that time is 1.8 seconds. Alright, we're looking for the EMF. That's going to be measured in volts. So EMF is the number of turns times the delta phi, which is the delta magnetic flux over the delta time. Now we're given delta time and we're given the number of turns. We just need to find that delta phi. From past experience, we know that the delta of anything is going to be the final minus initial. So let's rewrite the equation, the full equation. Delta phi equals BA cosine of theta. That is our basic equation for magnetic flux. That is, of course, final minus BA cosine of theta initial. Alright, let's go ahead and plug in our givens and solve this. Equals B was given to us as 50 microtesla. The area final, again, we figured that out ourselves, is 0.0059 meters squared. So there's that. And then again, cosine of 62 degrees, because they were trying to trick us with putting that 28 in there, but we know better because we are AP. That is our final minus our initial. Well, the magnetic field is going to stay the same, so 50 micro Tesla. And then we know we have a different area because our patient inhaled 0.002 meters squared. And then again, cosine of 62 degrees. Solving all of that will get you 9.15 times 10 to the negative 8 Webers, because that is what magnetic flux is measured in. Well, now that we have that, and we know our delta T and the number of turns, we can just solve the problem right here. So let's put that over our delta T, which is 1.8 seconds. We're going to multiply that by 200 turns. And again, we're solving for EMF, so that's going to be measured in volts. Your final answer will be 1.017 times 10 to the negative 5 volts. The book is going to be very sneaky, and it's actually going to round this up a little bit. They're going to call it 1.02 times 10 to the negative 5 volts. And if that's not bad enough, they're actually going to make it 10.2 microvolts. All three of these have the same value, so all of these are the correct answer. So thank you for watching. I hope this helped you out, and good luck.